Hi everyone, I'm Nicole Henderson, editor at the Web Host Industry Review, and I'd like to welcome you to another one of our WER webinars. Today's session is called Unlocking the Secret to QoS in the Cloud, the 6 requirements of your storage architecture, and will feature a presentation from Dave Wright, founder and CEO of SolidFire. I'll let Dave introduce himself in a moment, but before we go any further, I wanted to take care of a couple housekeeping items. First off, questions. We're going to save a few minutes at the end of the session for your questions. However, you can feel free to submit them throughout the session using the question function in the webinar software. As far as actually putting the questions to Dave, we're going to leave that until the end. If you do ask a question and it doesn't get answered because we run out of time, or maybe it's a bit too specific, rest assured that we will have a record of the questions and who asked them, and somebody will reach out to you via email after the webinar. If you have a question you'd rather ask outside a public forum like this, there will be some contact info on the last slide, and you can feel free to reach out that way as well. There will be a video archive of the webinar available if you want to revisit a certain slide or a part of the presentation or share it with somebody else. And it'll be available next week at thewer.com/webinars, so be sure to check that out. Now, without further ado, let's get started by turning it over to Dave.
Hi, this is Dave Wright. I'm the founder and CEO of SolidFire. So for those of you that I haven't met or haven't talked to you before, I was the founder previously of another cloud startup called Raidless. I did online backup and storage to the cloud and sold that company Rackspace and ended up spending about a year and a half at Rackspace helping them build and launch their cloud computing effort. So about 3 years ago, I left Rackspace to come and start SolidFire and help advance the way the world uses the cloud. So it's great to talk to you guys today. So we're going to kick things off by talking a little bit about quality of service and what it is and why it's important. So the definition that we've kind of written for quality of service is really the ability to deliver consistent application performance regardless of system condition or application activity. So if you think about the ability to have cloud customers have predictable performance, have a known level of performance, and have consistent performance regardless of what else is going on in the actual cloud infrastructure, that ultimately is what we see as true quality of service, the ability to tell customers what they're going to get and then deliver it consistently. If we talk about why this is important, why is it important to be able to define performance, to be able to deliver it consistently, it really is about the growth and adoption of cloud and the growth and the types of workloads and applications that the cloud is being used for. And what we're seeing is that the use of cloud infrastructure is moving beyond basic web applications and test dev and things like that into a much wider range of enterprise applications that have traditionally been run on dedicated or managed environments, and applications that are very often performance sensitive. And in a lot of cases, the traditional cloud computing infrastructure, whether it's using local disk or some kind of network storage, has really been challenged to be able to deliver the level of performance as well as the consistency of performance that's required for these higher performing and frankly higher importance business critical applications. And so that's ultimately why this is important, is because to get to that next level of penetration of a customer's business applications in a cloud environment, you really need to be able to deliver the quality of service. And you also need to be able to address the noisy neighbor issue. And this is something that obviously is both a perceived issue with cloud computing, but in many cases is a very real issue in cloud environments as well. The idea that on a shared infrastructure, one application or one tenant can consume more than their fair share of activity or can do something that is going to cause an impact to other users on the system. And this noisy neighbor problem is something that exists in all multi-tenant infrastructures. It's something that hypervisors have gotten very good at handling on the compute side of things. If you think back to shared hosting and everybody sharing the same kind of compute and memory resources on a host and the type of impact people would have from other busy applications, a lot of that was solved by moving to hypervisors, allocating compute and memory resources on a very fine-grained basis, and being able to deliver consistent compute performance to each virtual machine, regardless of what else is going on in the virtual machines on that system. Well, that same problem really exists in the storage realm today. Storage realm is basically the shared hosting environment still, where you've got everybody sharing the same resources. and one guy performing badly can affect everybody else on the storage system. So quality of service is certainly important as we look at kind of advancing the use cases for cloud computing. But I think it's important to note that some of the ways that quality of service is being done today, either by storage systems or by hypervisors, really isn't a great solution to the problem. And I'll talk a little bit about why before we go into the architectural requirements to deliver true quality of service. So if we look at the options that are available today, there are really two or three main ones that we see. So the first is prioritization, the ability to, typically within the storage system, define higher priority or lower priority applications. And it seems like a good idea at first glance because, obviously in an environment some applications will be more important, some applications will be less important. But the reality is there's two shortcomings here. One is that in a cloud environment, very often it's difficult to rank the relative importance of a set of applications. All of your customers think their applications are really important. Some may pay you more or less, but at the end of the day, it's very difficult to know any given set of applications what their relative priority should be. And furthermore, it's certainly possible that you have a bunch of very high priority applications that are fighting with each other for resources, and prioritization can't solve that problem. The other problem with prioritization is it doesn't necessarily lead to consistent performance. It does say that in times of contention, more important applications will get more or less performance than others, but it doesn't say how much performance that actually is and whether it will be enough for that application's requirements. So while it certainly may be better than nothing, it really doesn't give the consistent performance that we talked about needing for true quality of service. The second approach is rate limiting. And this is something that's available in a number of storage systems as well as a lot of hypervisor environments today where you can set an I/O limit on an application. And this seems like a good thing because it can prevent some of the noisy neighbor effects of one application consuming too much of a storage system's resources. But there are problems with this. So one of them is that it's only setting the limit. It's only setting the maximum performance that that application can have. It doesn't say anything about the minimum performance. It doesn't say anything about the minimum amount of storage resources available to that application. And so it's still very easy to get in a situation where not only can people not hit their rate limit, but they can't even get close to it due to other contention issues and other load issues on the storage system, fault conditions or other things that might affect that. The other problem with rate limiting is that it doesn't really reflect the real world nature of applications. And that is that storage applications or applications that use storage don't just run at a consistent level performance. They don't just run at 1,000 IOPS day in, day out, and that's all they ever consume. Storage applications are, by their nature, very bursty. They have periods of low activity and periods of very high activity. Things like database checkpoints, for example, that can drive a tremendous amount of activity in a very short period of time. Things like booting a virtual machine, where there's a lot of I/O very quickly, and then that virtual machine may sit basically idle. And the problem with rate limiting is that when you have a burst of activity, you can hit those limits very easily, and then you're capped in terms of your performance. Latencies go very high, and that operation, which is typically something you want to complete very quickly, like booting a virtual machine or completing a database checkpoint, now takes a very long time to complete, even though the rest of the time that application or virtual machine may not have been consuming very much storage resources at all. So rate limiting doesn't provide a minimum floor, and it also doesn't provide good performance for real-world application scenarios. The last way that we're seeing this addressed is some kind of tiered storage. So multiple types of storage media being used together either on a manual or automated basis to give varying levels of performance. The challenge with this is that it either requires manual placement, so you have to decide which tier of storage each application goes into, or it's automated and tries to select the hottest data to go in any given tier, and becomes very unpredictable because on a day-in and day-out basis, different applications, different tenants, are likely to be perceived by the storage system as the hottest applications, the more important applications. And that, by definition, means somebody that was hot yesterday may not be considered hot today, even though their workload may not have changed at all. So you now live in an environment where day-to-day, a customer's performance can vary significantly. Yesterday it was in the SSD tier and it had 1 millisecond latency. Today it's down on fiber channel disk and it has 6 millisecond latency. And what happened from that customer's perspective is simply that things just got slow and they don't know why. And so tiered storage and the unpredictable performance that comes with it is something that can, in many cases, make the problem worse rather than better. So let's look at what is actually required to guarantee quality of service. If the existing approaches today can't do it, what things do you actually have to do to enable this? And at SolidFire, we've taken a very close look at this problem and really identified 6 key characteristics, 6 key requirements for storage systems that need to be in place in order to be able to guarantee quality of service. And having a few of these is good, but the more of these they have, the better you can guarantee performance and the closer you can come to the ideal of being able to give a hard guarantee, a consistent guarantee on that performance, regardless of anything else that's going on in that storage system. And so that's what we want to spend the bulk of the time walking through today. So just really brief, all SSD architecture, a true scale-out architecture, Raidless data protection, balanced load distribution, fine-grained quality of service control, and performance virtualization. And we'll walk through these one at a time and explain what they are and exactly why that's important to delivering guaranteed quality of service. So the first requirement is all SSD architecture. And you might say, why not disk? What's wrong with disk? Why can't I deliver consistent performance off of disk? I don't need the SSD levels of performance. And the reality is most applications today don't need the full performance of what SSDs can offer. Only a small percentage of them do. So why is it so important to use SSD instead of disk? The reality is that this is the only way to deliver consistent latency for every I/O that occurs. Without quality of service, you have a situation where a lot of different applications converge on a single disk, and because that disk has a single read-write head, it can only service one of those I/Os at a time. The disk starts spinning the I/O head back and forth over the drive, serving one I/O at a time, and you have a very highly variable latency coming out of that drive as a result. And in periods of high contention, that may be 60 milliseconds or more of latency. In periods of low contention, maybe 5 milliseconds. But the point is that I/O activity in a multi-tenant storage system can be coming from any number of different applications. And from the perspective of the individual customer and their applications, all they're seeing is that their latency can vary greatly from time of day, from minute to minute, from second to second, because of things that are completely outside of their control. And with a spinning disk, there's virtually nothing you can do to eliminate this problem short of dramatically under-provisioning the system, making sure that there's absolutely no I/O contention at all on a single disk. It's impossible. Let's look at an SSD by comparison. An SSD architecture, by the nature of the SSD, doesn't have any moving parts. There's no physical bottleneck in the system. And in fact, SSDs are built with multiple chips and multiple parallel channels of I/O. And that means that multiple I/Os can be served in parallel. There's no seek latency between each I/O, so each I/O completes very, very quickly. And as a result, even when you have many I/Os coming in at the same time, rather than creating a queue or a bottleneck, you're able to deliver those I/Os with consistent latency and deliver 20 to 30 times the number of I/Os that you could with a disk-based architecture. So it's not just about delivering the individual I/Os very quickly. It's about being able to deliver consistent latency, which is the building block of any kind of quality of service. If you can't deliver consistent latency, you're going to see variable performance. You're going to see a wide range of application performance as a result. So the second result is that the second requirement is a scale-out architecture. So scale-out refers to the idea of building a storage system rather than the traditional method of using controllers combined with disk shelves for capacity, where you add more shelves to get more capacity, building a storage system with a set of nodes that have essentially controller capacity, performance, memory, network connectivity, as well as storage capacity, and then scaling those nodes as the system grows. And there are storage systems in the market with both of these approaches today, although the controller-based approach is still the predominant architecture, particularly for block-based storage systems and performance-oriented storage systems today. And the reason for it is that it's by far the simpler architecture and the one that's been with us for the longest period of time. But let's look at why that's a problem. So if we look at a controller-based architecture here on the left, we've got 2 controllers, and then we've got 3 disk shelves of varying sizes, a green, a red, and a blue shelf. And what you find is that we start with a system that has the 2 controllers and the green disk shelf. And that gives us a certain amount of capacity and a certain amount of performance. Now, as the system grows, as we add another disk shelf, in this case the red disk shelf, we've added more capacity, potentially about the same amount of capacity, but from a performance perspective, we've added less performance. Well, why is that? Because we haven't added any more controller resources. Those same controller resources are now having to service I/O for a larger pool of disks. And even if those resources weren't completely bottlenecked to begin with, they're not going to be able to deliver the exact same level of performance across all of those set of disks that they did on the first one. And the problem only compounds itself as the system grows. Each set of disks you add to it, the controller becomes more and more the bottleneck to the point where eventually you're adding capacity, but you're not getting any more performance. And this unpredictable scale of capacity and performance makes it very difficult to build a storage system that can give consistent quality of service and consistent performance guarantees. Because on your first disk shelf, you might have been able to deliver 100 IOPS per gigabyte, but by the time you're to your third or fourth shelf, you might only be able to deliver 20 IOPS per gigabyte. And that applies not just to the new disks you added, but the customers that were on that first set of disks to begin with. And so you have to provision performance very conservatively. You have to really provision performance that's going to be associated with your worst case performance on the system, as opposed to be able to grow with consistent linear scale. By comparison, a scale-out architecture like SolidFire gives you a consistent amount of capacity and performance for each node in the system. So the first node you add, the second node you add, and so on and so forth, you're getting more capacity and more performance in a consistent, predictable fashion. And this means that when you're provisioning out performance for quality of service, you know that you're going to have that same amount of performance on day one that you will, 2 years later as that system has grown to a significantly larger capacity. And that's very important, because if you don't have that predictability, you're not going to be able to guarantee the quality of service like you want to. So let's talk about the third requirement for consistent quality of service and guaranteed quality of service, which is RAIDless data protection. So RAID is certainly the most well-known data protection scheme used in storage systems today. It's been with us for almost 30 years now, and is used by almost every storage system in the market today. And it's used for the fact that it's relatively simple, it's very inexpensive, and at the end of the day, it does a pretty decent job of providing data integrity. But the problem is the way that it provides data integrity doesn't necessarily lend itself well to providing consistent performance. And I'll give a couple examples before we go through the illustration here. As you may know, there are many different flavors of RAID. You've got RAID 1, 2, 3, 4, 5, 6, and so on and so forth. You've got vendor-specific versions and flavors of RAID. But almost all of the RAID types out there today have the characteristic that they spread redundancy around a very small set of disks. Whether it's a RAID 5 system where you might have, say, 5 disks with 1 parity disk, or it's a RAID 6 system where you might have 12 data disks and two parity disks, or 14 disks with the parity spread between the disks, or even a RAID 1 or RAID 10 system where you have 2 disks that are mirroring each other. There's a very small amount of disks that are sharing redundancy information. And where this becomes a problem is when you have a failure, and what happens when that failure occurs. And the problem with RAID-based systems is that when you have failures occur, the remaining drives in the system suddenly have a lot more work to do than they did before. And the reason they have a lot more work to do is that they not only have to deal with servicing the I/O that's continuing to come in, they're having to deal with any of the I/O that was directed to that drive. And that I/O that was directed to that drive, depending on the RAID scheme, is now going to double the load on another drive in the case of a RAID 1 or RAID 10 system, or is going to incrementally increase the load on every other drive in the system in a parity-based scheme. So in a RAID 5 scheme, if you have, say, 7 drives or 6 drives in your RAID set, every I/O, every read coming to that system is now, rather than going to the one failed drive, having to go to every one of those other drives to rebuild the parity information. Every write has to go to every one of those drives. And so you have a compounding effect from the one I/O that's being done to I/Os across many, many drives. And that leads to a reduction in performance as a result. However, beyond that reduction in performance, we now have a problem where we have to rebuild that failed drive. We have to take the data that was in that drive and put it on another drive, typically a dedicated spare drive. That now creates a new bottleneck. We have to take all of the data off of all of the other drives in that RAID set. We have to read all of that data and put it into that one remaining drive. And so now you have all of the load going on to read all the data from all of those drives in that RAID set and put it in one remaining drive, all while we're trying to serve I/O, all while we're trying to handle parity and other information that's needed to continue to have the system function. And the net result of this is that when you have a failure occur, you get a significant drop in performance, often 50% or more, while that rebuild is in process. Furthermore, that performance drop will often be imbalanced across the system. Because the RAID is typically done at the level of, for example, a disk shelf, only I/O going to that shelf is affected. You have other I/O in the system that isn't affected, but depending on how a customer's volume provision, they may have a severe performance impact, or they may not see anything at all, but it's not predictable, it's not consistent, and so it's very hard to wrap any kind of quality of service around that, or even to explain to a customer whether they're going to be affected by a failure or not. The other problem that you see with this approach is that the performance that you're getting can be highly irregular. And it can be irregular for a very long period of time as that system rebuilds. Typical RAID-based systems with large capacity drives take many, many hours to rebuild. And during that time, you're getting irregular performance depending on the load and the other things that that system is doing. Again, that can occur for 6 hours, 12 hours, in some cases 24 hours or more with very large drives. And this is something you see on high-end systems, low-end systems. It really doesn't matter. The only way to address it is to dramatically, again, under-provision the performance of the system so that the overhead from rebuilding is not something that's going to cut into your active I/O. But even then, there's going to be typically a visible impact. And fundamentally, this impact from failures is something that is at odds with delivering consistent quality of service in a cloud environment. Because in a cloud environment, the customer is not exposed to the underlying hardware. They're not exposed to RAID failures and RAID rebuilds. They can't see the storage controller UI. They don't know what's happening there. And frankly, even if you could surface to them, it's really something that they don't want to have to think about when they're in a cloud environment. They simply want something that's always on, always working, and always delivering consistent performance. So let's look at how SolidFire's data protection gets around this. With the SolidFire architecture, we distribute the redundancy information for an individual drive across every other drive and every other node in the cluster, rather than having it concentrated on a single RAID set or a single partner drive. Furthermore, when a failure occurs, we can rebuild by sharing data between individual drives in the cluster in a node-to-node, peer-to-peer, mesh-based exchange. So rather than have to rebuild from an entire set of drives into one drive, every drive in the system exchanges a small amount of data with each other. The result of this is that when that failure occurs, only the I/O going to that one drive is affected, and we can redistribute that I/O evenly across all the remaining drives in the system. And as we rebuild from that failure, we can rebuild in parallel across all the drives in the system. We don't use any dedicated spare drives. We don't rebuild into a single bottleneck like that. We rebuild into the free space on all the remaining drives in the system. The result of this is that when a drive fails, you only lose the capacity and performance proportional to what failed. There's no outsized loss of capacity and performance. And also, the loss of capacity and performance is balanced across the entire system. You don't have this highly irregular loss from one customer to another. And as the system rebuilds, it rebuilds very, very quickly. We can rebuild from a failure in a matter of minutes instead of hours or days. And so you get a situation where the failure occurs, the performance impact is minimal, the rebuild is very quick, we restore the full level of redundancy, and typically nobody is even aware that a failure has occurred. And this ability to go beyond the limitations of traditional RAID, deliver consistent performance even when failures occur, is critical to be able to deliver consistent quality of service. Because quality of service is not something you can say, you'll get this performance most of the time as long as nothing ever fails. Because things do fail. At large scale, they fail all the time. And if it's something that's going to be a serious impact to that customer or to a large number of customers, it's something you have to deal with. And this is really, we feel, the only way to deal with that successfully. So let's talk about the fourth requirement for guaranteed quality of service, which is a balanced load distribution. And only with a balanced load distribution can you eliminate hotspots that create unpredictable I/O latency. We talked about how disks can create unpredictable I/O latency, but the problem, even with an SSD-based system, is that if you don't balance the load across the entire system, if you allow hotspots to develop, you can still create bottlenecks where individual I/Os, individual volumes, see significantly different latency than what everything else on the system is getting. And again, this is particularly relevant in controller-based architectures where an individual volume is spread across a relatively small number of disks in a single disk shelf. And you can very easily get into a situation where individual shelves of disk have obviously different levels of capacity utilization, but also highly variable amounts of performance utilization. So in this illustration, the shelf in the middle is completely maxed out in terms of performance. There's very little headroom available, even though the other volumes in that, or the other shelves in that system, still have performance available. And what this means is that the customers that are on that set of volumes are having performance issues, while other people in the system aren't seeing any issues at all. And there's still, from the perspective of the system administrator, there still seems to be headroom available, but the reality is this particular set of volumes, this particular set of drives, is actually fully maxed out. And getting rid of these hotspots ends up being typically a very manual process. Typically it involves manually moving volumes from one set of disks to another in order to rebalance the load distribution. And that kind of manual balancing effort is really just not something that can be done at scale in a cloud environment, because load is changing constantly, applications are coming on board constantly, there's typically a large number of these systems that are being deployed. Having to manually troubleshoot, figure out where the bottleneck is, move volumes around to alleviate those bottlenecks is really just not realistic. But if you don't have that balanced load distribution, eventually you are going to end up with bottlenecks in place. And again, the only way to avoid it is to dramatically under-provision the system. With SolidFire's approach, we use an approach where we distribute both the capacity and the load evenly across the entire system. There's no manual placement of data. There's no limited range of data or limited range of nodes or drives that the data is placed on. It's distributed evenly across the system in a way that keeps capacity and performance balanced across the entire system, so you don't hit a limit one place while still having plenty of capacity and performance somewhere else in the system. There's no manual balancing effort required. It's something that's as simple as looking at a gas gauge and seeing how full you are from the capacity perspective and how full you are from a performance perspective. And you know that as long as it says you have headroom available, you can continue to add more applications. And that ability to balance the load distribution evenly, deal with changing workloads, new workloads coming on board, and keep it balanced is really critical to deliver consistent quality of service, because you want to know when that system is going to be full. You want to have predictability in terms of when that system is maxed out. And if you don't have that predictability, if you have unpredictable I/O latency, even when it seems like there should be more performance available in the system, you're going to have a very difficult time delivering that consistent performance and that consistent quality of service. So the fifth requirement for guaranteed quality of service is fine-grained quality of service control. And we talked a little bit before about rate limiting, and rate limiting is an example of coarse quality of service control. I kind of call it the quality of service sledgehammer, if you will. It basically says, hey, here's a maximum, you can't go over that. But the reality is most storage workloads do go above that. And most storage workloads need more performance from time to time than any given arbitrary limit. And if you set the limit so high that they'll never reach it, then really you're allocating more performance in that application needed, and you're going to have a difficult time provisioning and managing performance. You're essentially over-provisioning performance. So what we really have done with SolidFire is tried to deliver a fine-grained quality of service model, one that gives you complete control over the level of performance in the storage system at any given time. And in this illustration, what we're showing is how SolidFire's burst capability works. So SolidFire's quality of service control certainly has the idea of a maximum, but it also has the ability to set a separate burst limit. And the idea is that an application that's running under its maximum can then, for a period of time, burst above its maximum to a separately configured burst limit. And that bursting capability allows applications that have bursty workloads, which is the majority of storage applications, to be able to accomplish those bursts very quickly, to complete that in a very short period of time, keep latencies low, and continue to function on an ongoing basis. And without this ability to have burst and have this fine-grained quality of service control, you have something where, yes, you may have a level of quality service in terms of a maximum level of performance, but customers are constantly running into problems with their application where they have latency spikes that are causing application problems because they're running up against this limit, even though from their perspective, when they look at a longer time period, they don't seem to be running anywhere near their maximum. And that's where rate limiting really gets you into trouble, is customers that look at their utilization and say, hey, I'm paying for 1,000 IOPS, you've got my limit set of 1,000 IOPS, my average is only 100 IOPS, and yet anytime I have a database checkpoint, my latency goes through the roof. What's going on here? And this ability to control burst is one that, and allow for burst, is one that removes a lot of the issues around coarse-grained quality of service controls. But it's important to point out that the ability to burst doesn't mean that you can run above that all the time. The fine-grained quality of service control means that it really is a limited bursting capability. If they try to exceed their maximum for an extended period of time, they're still back down to their maximum, and they can run at that level that's been allocated to them, preventing them from, again, becoming a noisy neighbor. Without this level of control, it's very easy to create noisy neighbors, allow them to consume all the performance that's available in the system without any impact to the other customers. So now we're at the sixth and really final requirement for guaranteed quality of service, which is performance virtualization. So what is performance virtualization? This is really kind of a new term, something that hasn't really been used a lot in the storage industry before. You may have heard of storage virtualization, which is really a different concept, typically having to do with aggregating heterogeneous storage systems. So what is performance virtualization? Well, the way to think about performance virtualization is the same way you think about CPU virtualization. The ability to take a CPU, which has a known constrained set of performance, and divide that CPU into multiple virtual machines, either on a core-by-core basis or in some case a megahertz basis, to deliver a consistent set of performance to each virtual machine. And this is something that has been done on the compute side for a long time, but has never really been present in the storage side of things. There was really never a way to control and provision performance separately from capacity. If an application required a certain level of performance, previously the only way to deliver it would be to allocate a certain amount of capacity across a certain number of disks, that individually the disks had a certain level of performance, running a certain RAID level, and in aggregate all of these components would deliver, you would hope, the required level of performance. But it wasn't exact science. It was very difficult to deliver any guaranteed or consistent level of performance. You would either undershoot it or overshoot it. And if you were sharing the same set of disks between multiple applications, there was really no ability to deliver a known set of performance on a consistent basis. Because storage performance was never a first-class citizen. It was never what you provisioned out. You provisioned out capacity. You might provision out capacity in one tier versus another tier, but you weren't really provisioning performance. You were always thinking about provisioning in terms of capacity. You really only had one dial to work with. So the idea of performance virtualization is to separate capacity from performance, to make them independent entities, make them both first-class citizens, and allow you to provision them independently. Allow the storage system to hide the complexity so that all you need to do is provision the capacity that's required and the performance required, and allow you to provision those two things independently. Because in storage systems today, you provision capacity, and you really don't know what you're going to get at the end of the day for performance. With performance virtualization, you provision your capacity that you need, you provision your performance that you need, and the storage system itself, just like the CPU hypervisor, delivers that level of performance on a consistent, ongoing basis, and is responsible for isolating applications from each other, just like the CPU hypervisor does, to be able to deliver that performance. The other advantage of performance virtualization is that much like a CPU hypervisor, that performance allocation can be completely dynamic. And just like a CPU hypervisor, you can allocate more or less CPU resources to an application without, say, changing its memory footprint. With performance virtualization, you can allocate more performance to an application without changing its capacity footprint, and without having to manually place the data on a different tier of storage or a different storage system. And this performance virtualization is absolutely key to delivering quality of service, because with quality of service, if you have to play guessing games around the amount of performance that's going to come out of a given volume, you're not going to be able to guarantee that. You're not going to be able to deliver consistency, and in reality, it's going to change on an ongoing basis. And if a customer needs a different level of performance, if they need different quality of service, there's now a large amount of manual effort that's required to get them to that level, if it's even possible. So really, only the capability of performance virtualization, decoupling capacity from performance, will allow you to make quality of service a first-class citizen, something that you can feel confident selling to customers, provisioning for individual applications, and guaranteeing on an ongoing basis. So those are the six requirements. And really, just in summary, we really feel that guaranteeing performance requires all six of these. Without these, there is going to be some scenario and there's going to be some situation out there that you're not going to be able to provide that guarantee. whether it's a RAID-based architecture that prevents you from providing a guarantee when failure conditions occur, or whether it's lack of fine-grained quality of service controls that don't allow you to deal with bursty workloads, or a disk-based architecture that simply can't deliver consistent latency. Without all 6 of these, you're going to have to do some amount of complex manual effort, typically involving over-provisioning or manual management, to deliver quality of service. And even then, it's going to be difficult to deliver consistently. Secondly, we talked about how bolted-on quality of service features, the very basic levels of quality of service that are available in some storage systems or hypervisors today, really aren't the right solution at scale. They don't allow you to get the level of consistency and performance that's needed to offer performance guarantees. So the third thing is that this ultimately is the way things are going. The cloud of tomorrow is not going to be the cloud of today and the cloud of 5 years ago. It's not going to be a wild, wild west where you put your applications out there and they fight for resources and you get what you get because it's cheap. The reality is that the cloud of tomorrow is going to be just like virtualization, something that started as a very kind of simple operational and kind of implementation advantage, but showed value for production applications and therefore evolved into something that could deliver the quality of service and the SLAs needed for production applications. Cloud computing is going to evolve very much the same way. The high-performance applications are moving to the cloud, and they're going to require both the higher level of performance as well as the guarantees that the quality of service capabilities provide. And the applications really will only move there once these capabilities are available. So at the end of the day, it's really about enabling applications to run in the cloud, to have guaranteed quality of service, and to be able to give customers the peace of mind that those applications will have the resources they need and do it in a method that has really never been possible before. So that is basically the presentation for today. Obviously, we are certainly describing a lot of the characteristics of the SolidFire storage system. We haven't gone into detail on SolidFire and the functionality and capabilities that we have, but all of the architectural elements that we talked about today are things that are embodied by the SolidFire storage system. And you'll find bits and pieces of these architectural elements, whether it's the scale-out piece, the all-SSD piece, or the kind of Raidless data protection. You'll find bits and pieces of these in other storage systems, but we really think that SolidFire is the only storage architecture that has all of these capabilities today and can guarantee quality of service in a cloud environment. So we appreciate your time. We'll go ahead and turn it on for questions now. But certainly if you have any other follow-up that you'd like, if you'd like more details on SolidFire and the capabilities that we have for guaranteed quality of service, we certainly would encourage you to follow up with our sales team, and we have the email and phone number for Tom Troy who helps you out right there. So let's go ahead and see if there are any questions, and go ahead and open it up. If you haven't asked your question, or if you have a question you'd like to ask, go ahead and type it in the chat window, in the Q&A window, and we'll try to get that answered.
Okay, great. Thanks a lot, Dave. It looks like we have a few questions here. The first question is from Rob, and he has a question about IOPS. How many IOPS do applications need, and do you have an example you can share to give us a reference?
Yeah, so that's a good example. That's a good question. In a lot of cases, the ability to now provision performance, which wasn't really possible before, raises the next question, which is how much performance do I need to provision? In a lot of cases, customers may not even know. They may come to a cloud environment and say, I need performance. And if you ask them how much performance they need, they say, I don't know, but I probably need a lot of it. And so that can create, again, having this capability can create both new opportunity, but also potential for confusion. And so, we've done a lot of research. We have a lot of data that we can help service providers with that give essentially typical levels of performance requirements for individual applications, whether it's a SQL Server database, whether it's a Hadoop instance, whether it's a web server, whether it's VDI instances. We have a lot of the data that we would consider best practices for that on an application basis, as well as information on the amount of data reduction and other things you can get out of those applications. For example, a VDI instance would typically, for a low-performance VDI instance, maybe require somewhere on the average of 50 IOPS on average, and maybe 150 IOPS for a very high-performance instance with some amount of burst above that. So we have data for a lot of these types of things. But the other key advantage of SolidFire's dynamic quality of service capabilities is that you don't always have to answer that question right out of the gate. Our ability to change the performance over time means that a customer who is aware of their application's requirement can deploy it with one quality of service profile. Maybe they deploy it with 1,000 IOPS, and then look at what it's actually consuming. Is it consuming some amount less than that, in which case they can dial the allocation back, or is it consistently maxing out that allocation and they need to dial it back up? And that ability to start at one level, move up or down as needed, or as conditions dictate. For example, maybe an e-commerce site that has a very busy holiday season and wants to dial up the performance during that season. That's one of the key advantages of this performance virtualization capability that just isn't possible in a traditional storage system. You have to get that sizing right to begin with, because if you get it wrong, the only way to do it is to typically change out hardware. And that obviously is very burdensome. And so we actually can make the sizing conversation for cloud customers a lot simpler than it is today, and allow customers to get right-sized a lot more quickly than they would otherwise.
Okay, great. I've got a question here from John. He has a question about rate limiting. Doesn't rate limiting allow you to achieve quality of service?
Well, there are certainly folks that are calling rate limiting quality of service, or are advertising quality of service features that, when you boil them down, are really glorified rate limiting. And it can allow you to achieve a consistent level of performance in a constrained set of parameters. But there are a lot of conditions where you won't get that. And for example, the example I used earlier, where the system just isn't able to deliver that rate limited level of performance because it's been over provisioned, there's too many users on it, or there's simply a failure occurred that has reduced the overall capacity of the system. So rate limiting is an interesting tool, but it really doesn't achieve the guaranteed quality of service capabilities, as well as the ability to deal with more real-world application needs.
Okay, thanks. Ken has a question about SSDs and their reliability. He says, I've heard that SSDs are unreliable and wear out quickly compared to regular disks.
Yeah, I think that's a common, I don't know if I want to say misconception about SSDs, but it's certainly something people are concerned about, because somewhat differently than disk, SSDs and flash memory does have a limited number of write cycles. The reality of the situation, though, is that when you design a system from the ground up like SolidFire has, there are a number of things that you can do to really mitigate the issues related to wear on the SSDs. Most of the issues related to wear on SSDs come from treating an SSD like a disk, which it isn't. It has very different characteristics for how it reads, writes, erases, and manages data. And when you treat it like a disk, you can create a lot of what's known as write amplification. You can wear that disk much more quickly than the relative amount of data that you're writing to it. SolidFire's architecture is designed to essentially be very, very friendly to the SSDs. And also the fact that it's an all SSD system means we get to spread the wear and spread the load out across many, many SSDs. And so as a result, wear really just isn't something that is a concern in our system, and we warranty the drives for 5 years as a result. The other question about reliability outside of wear is what is more reliable? And the reality is that actually SSDs are actually far more reliable from a failure and an annual failure rate perspective than spinning disk. And the reasons for that are fairly obvious. You've got no moving parts. Spinning disks typically have a failure rate between 1% and 2%. The SSDs we use have a failure rate of typically 0.25% annual failure rate. And so from just the perspective of how often that drive is going to fail for other reasons, SSDs are actually significantly more reliable than disk. You've got less drive replacements and concerns than you'll have with a spinning disk today.
Okay, thanks. Barry has a question. He's asking you to explain the Raidless architecture and how it writes when a drive is lost.
Yeah, so that's a good question. So the Raidless architecture for SolidFire is based on placing redundant copies of data throughout the cluster, but done in such a way that two drives aren't exactly mirroring each other. The data that's on one drive, the redundant copies of that data are spread throughout the remaining drives of the system. So when a drive is lost, actually what we do within the SolidFire system, and we haven't, again, talked a lot about the SolidFire architecture, but we have in each node, so each of the scale-out nodes in the system, we have an NVRAM card. And that NVRAM card is used for a couple of different reasons, primarily as a write cache, a place for data to land and be written and committed very quickly, write latency very low. and we replicate the data to multiple NVRAM cards, so multiple nodes within the system as a write comes into the system. And then in the background, we push it out to the individual SSDs. And then after it's been pushed to the SSDs, we can remove it from the NVRAM. This provides a number of benefits to us, including reducing wear on the SSDs, including the ability to deliver consistent latency, even if individual SSDs are having latency spikes due to garbage collection. But it also comes into play when there's drive failure. Because when a drive fails, what we can do is keep the data that's been written safe in the NVRAM. Any new incoming data can go into the NVRAM temporarily. And then we can determine, once we determine whether that drive is going to come back or whether it's going to be completely dead, where to place that data. And if we make the determination that that drive is dead and is not going to come back, what we will do is take that data that was on that drive and, again, redistribute it to the remaining drives in the cluster. And that means that all the data that was coming in that was written in the NVRAM, it basically has a new home as well. And it will get pushed out to those other drives in the cluster as well. So data is still protected when a failure occurs. New data that's being written in is being protected and is pushed out in the background to other drives once we've made the determination that that drive is dead. But the key thing here is if you look at write latency, the fact that that drive is unavailable or has failed isn't visible to the application because the application is only writing into, from its perspective, that NVRAM. That's the latency and consistent performance that it sees, regardless of whether a drive behind that may have failed or not.
Okay, great. Justin has a question. How does IOPS relate to latency in the SolidFire solution? What is the average latency when looking at, say, random 4K RW?
Yeah, so that's a good question. So there is a very specific formula for relating latency and IOPS. And some of you may know that basically latency, IOPS, and QDEF, the three of those properties are all related by a mathematical formula. And when we look at latency in a SolidFire system, we set the quality of service parameters based on IOPS. Those IOPS actually translate into latency numbers. So the latency you'll see depends on the load you're placing on the system as well as your IOPS parameters. Typical latency, though, if you're not bumping up against your limits, is a millisecond or less. So again, dramatically faster latency than you'll see in a disk-based system. And in almost all cases, less than 5 milliseconds latency, but typical latency of a millisecond or less.
Okay, thanks. And we have one last question from Karen. She has a question about noisy neighbors. My current SAN vendor tells me that the noisy neighbor is not really an issue. Can you clarify briefly for me again?
Yeah, so we've definitely heard people say, well, you know what, I don't have that issue on my system, or my vendor tells me that's something I don't need to worry about. And that's usually not the case. And what I mean by that is that sometimes it's not obvious that is an issue, or it's only not an issue because the system isn't very heavily loaded. Obviously, if you've got lots and lots of headroom and an individual customer can't consume a significant amount of the headroom that you have available in the system, then you're less likely to see issues related to this. But as that system fills up and as the load increases, the impact of an individual customer can be magnified significantly, and you can start to see this impact very dramatically. And this is something that I've seen in the real-world scenario in many different service providers where they don't think they have any issue with this at all until they have it. And then once they have it, typically because they've tipped over some performance threshold that may not be anywhere near what they perceive is the limit of the performance of the system, but simply that they've gotten high enough that an individual customer can now begin to dip into that reservoir and cause problems for other customers. Once they tip over that, it suddenly becomes a constant issue, something that they basically are constantly putting out fires on that storage system, constantly having to migrate workloads away, isolate customers on their own set of disks, or do other things in order to prevent it from becoming an issue. So it's something where sometimes you won't see it early on, but over time as the system fills up, suddenly becomes a very urgent and pressing issue. And again, the ways that people deal with it, again, there's very hammer ways to deal with it. In some cases, it'll be, hey, I've noticed this customer is causing problems. We're going to put a rate limit on him. We're going to prevent him from doing that. Or, hey, this customer has a really important application. They're being impacted by other customers. We're going to put them on a dedicated set of disks. But it's important to point out these approaches really are sledgehammers. They're not scalpels. There's not something that can be applied on a fine-grained basis, on an automated basis. There's something that requires manual diagnosis and manual action to deal with. And that's been done in the enterprise storage world for a long time. It's just what people are used to doing, and that's why storage vendors will tell you, look, this is the problem we figured out how to deal with. but the solutions they have for dealing with it are not solutions that scale in a cloud environment. They're not things that can be automated. They're not things that can be done without administrator intervention. And they're not things that can be done imperceptibly to the end user in most cases. And so a lot of times what they consider solutions for noisy neighbors really don't provide a workable answer. All right, anything else?
No, that's about all the time we have for today. I'd just like to thank everyone for attending and for submitting your questions. Lots of great questions. And of course, I'd like to thank Dave for introducing the key elements in a storage architecture that provide quality of service in the cloud. So thanks again, everyone. Have a great day.